Good evening. Today we are going to see the problems which we have in exercise number 4. So till exercise 3 we have already uploaded the videos and hope you have solved the problems. Now we will go with exercise 4, and in this exercise 4 we have first problem. The compressive load P is transmitted through rigid plate, and you can see the diagram. And this area is given 3000 mm square for each bar. E is 45 GPa, and then we have to calculate the downward displacement of the rigid plate, and value of P is given as 400 kilonewton. So in this middle bar we have that is 1 millimeter shorter than other two. So first your outer bars will be displaced by or deformed by 1 mm or shortened by 1 mm, and then after shortening by 1 mm, then we have plate which will share the load will be shared by all three. Now, in this 1 millimeter, load will be shared by these two only, that is outer bars only. And then we will calculate that value. So we have bars in parallel. So this data that is given, and then deformation we have PL upon AE. Area we have mainly 2 into 3000 because we have these two bars. This is one outer bar, and second we have this. These two bars we have to shorten first by 1 millimeter, and for this we require 180 kilonewton load. So when we have plate over here, then in that case we have that load as 180 kilonewton. So we are now over here. So we have now plate here. When 180 will be subtracted, and we have load balanced that as 220 kilonewton, and now load we have on this plate over here 220 kilonewton. And now in this case your load will be shared by all these three. So this 220 kilonewton will be shared by 1, 2, and 3 bars. And first, that is to shorten outer bars by 1 millimeter, load required is 180 kilonewtons. And then we have delta L, that is deformation, will be PL upon AE. Now in this you can see we have 3 bars, and therefore we have deformation 0.181 millimeter. So total displacement or total deformation we have 1 plus 0.81, so 1.81 millimeter downward. So we have this will be 1.81 millimeter downward. Next we have this problem we have taken from IES 2019, and in this we have given two tubes. You can see we have two tubes. So first tube we have that is of steel, and we have this distance that is 150 millimeter, which will be inside, and outside we have that is 170. And for brass we have outside 170, sorry, inside 170 for brass, and 190 we have outside. And then if we will go with step by step, again bars are in parallel. Area of steel we have pi by 4 into 170 square minus 150 square. And we have area 5026.55 mm square. And area for brass actually. So we have this is area for brass, and we have this value that is equal to 5654.87 mm square. Then we have PL upon AE, that is of steel equal to brass, and from this we are going to get the relation between steel and brass, and that relation we will get it as 1.78 pb. So PS equal to 1.78 pb. Total load we have 1000 kilonewton. So PS plus pb equal to 1000. And from this we will get 1.78 pb plus pb equal to 1000. And pb we will get it as 359.71 kilonewton. And if we multiply it by 1.78, it comes 640.29 kilonewtons. So now we have to find out stress. We know stress equal to load upon area. So load now we have for shared by steel is 640.29 into 10 raised to 3 upon 55. So it comes 127.38 MPa. And sigma B we have PB upon AB. And then we have this value that is 63.51 MPa. So we can have this area of steel 5026, and area of brass we have that is 5654.87. And then from this we are going to get sigma B 63.61 MPa. And then we will substitute value for deformation PL upon E, 640.29 into 10 raised to 3 into 140 upon 5026.55 200 into 10 raised to 3. It comes 0.089 millimeters. If we will use, so this we have calculated actually by using steel. If you calculate it by using brass, then you have this as 359.71 into 10 raised to 3 into 140 divided by 5654.87 into 100 into 10 raised to 3. And from this you will get this value again 0.08 millimeters. So you can solve it by using steel or you can solve it by using brass. From both you are going to get same value. And then we have third problem now. This is most important one which was asked in IES 2017 actually. Now in this one we have given, so this is 30 millimeters, then we have this as 60 millimeters, and then we have 200 millimeters. Now they have given 180 kilonewton load is applied. So we have applied 180 kilonewton load axial along the length. So this is 180 kilonewton load is applied. Then they have given that 200 mm so cross section, and 200 length is restrained from expansion along its 300 by 200 so 300 by 200, so we have this portion, so this is restrained for, so expansion along its 30 by 200, so 30 by 200, so along this we are going to restrict its dimension. So this portion we are going to restrict 30 by 200 side by surrounding material. And therefore now we will go with this. So we are going to get this, if I will consider it as X, then I will consider Y, and then we have third, this is Z. Now along Y we have no change in length. We are not allowing it expansion along its 30 by 200. So cross section and 200 length and is restrained actually, and is restrained from expansion along its 30 by 200 side, means these two sides we are going to restrict or restrained, and therefore we are going to get change in length along y direction 0. So now sigma x we will get p by a, which is compression. But now what will happen due to this compression, my length, that is if I will say this is 60 so this is going to be increased. Now to decrease it or to keep it in the same position, so due to this compression 180 kilonewton, my 60 will increase. Now how much it will increase? Then delta t by t is equal to mu delta L by L is equal to 0.3 sigma by E. By this much amount it will increase. Now I have to restrain it, and for this restraint how much value we will require? So sigma y stress we will apply on it. So we will apply sigma y. And how much value we require? Delta t, that is equal to sigma yt upon E, or I can say sigma t by t is equal to sigma by E. So to reduce this, because we have to make it 0, this is increase actually if we will keep free. Now we have restrained, that means we require sigma y value to restrain it, to decrease it, means again compression. And then we will equate this value of equation 1 with value of equation 2, and that will gives me value of sigma y, which will be again 30 MPa compression. So we have sigma x 100 MPa compression, and sigma y we have 30 MPa compression. Alongside we are allowing increase in dimension or change in dimension, so we need not require to find value of sigma z. So sigma y actually that is developed due to restrain the 30 by 200 side. And then we have epsilon x 1 by E sigma x minus mu sigma y. So we have compression, so minus 100 it comes minus 91 by E, which is decrease value. So epsilon y we will get it as 0. Already we have seen it, we have restrained it. And then epsilon z, we have increased because we have compression from both x and y, and therefore it will increase your z, which will be 39 by E. And then volumetric strain, we know epsilon x plus epsilon y plus epsilon z, and it comes minus 52 upon E. That is volumetric strain, means we have delta V by V. So if you want to find out value of delta V, then you will get it as 52 upon E into 30 into 60 into 200, and that will gives me value of delta V, and minus sign shows your this value will decrease. Now E we know 2 into 10 raised to 5, so this 200, then we have 1 2, and then we can have again 1.6, and then we will get it as 52 into 1.8, so 36 3 93.6 minus sign millimeter cube. This will be decrease in the volume of body. And then delta L by L, we have epsilon x minus 91 upon 20,000, 2 into 10 raised to 5. And then delta L, we will get minus 0.091 millimeters. And then delta B by B, we have 39 upon 2 into 10 raised to 5. So 39 into 10 raised to 3. So it comes 5.85 10 raised to 3 minus millimeter, 10 raised to minus 3 millimeters. So likewise, we have these problems which we have to actually solve in exercise number 4. So today we will stop here only. So exercise 5 we will see in next video. Thank you.